Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 59, we will continue with urban flood management and drainage plans, and this is the second part. So, in this particular lecture, we will look into 1D and 2D dual drainage approach. Then we will conduct flood modeling using HEC-RAS. We will show you an example of that, and then we will do a case study. So, in 1D 2D dual drainage approach, we use 2D shallow water equations for surface flow and 1D for channel flow, and we can also model both pluvial as well as fluvial flooding. So, in this particular case, we will show you a case study, and I will show you an example of how we can use the HEC HMS and HEC-RAS software. And this we have discussed that these are two again free softwares which are also utilized, and usually we can conduct some like in this particular case we are considering that if there is a river or any kind of stream, and then we consider at certain sections we take we know the profile of the stream, of course, and we based on that we can determine that at certain sections what would be the total amount of flood that can happen in this. And once that happens, this water will come out of the banks of that particular stream, and then it will spread into the surrounding areas, right, and that will lead to overland flow, which actually creates flooding in that surrounding area. So, that is what could be modeled using this particular approach, but the basic thing is this channel could be even a storm sewer as well, and then using 2D overland flow we can model how the water at each of those nodes actually is spreading into the surrounding area. So, this modeling system involves not one but actually 4 softwares, but nowadays we can use only 2, and that takes care of the other parts. I will explain. So, the first part is this first software is the HEC HMS, and this is used for developing the hydrological model of the watershed, and using this we can develop the basin model, the meteorological models, and we can also put in the control specifications. And the data required to run this model is land use, land cover, the soil group, the curve number, the watershed, infiltration and time of concentration, then composite curve number for each sub basins, and those could be generated using this particular model. And then we can control the run of the model or the simulation by changing the duration and the time step in which it is run, and we can have different infiltration and flood routing procedures in this model as well. So, different infiltration actually refers to CN method or Horton, and then flood routing procedures are again are we following kinematic wave or diffusion wave and so on. So, those are the routing procedures. So, this is what is similar to what SWMM does more or less. So, that is the HEC HMS could be called as an alternative to SWMM in certain cases. Then in addition to this, we have got something called a HEC and GeoHMS, which is the Geospatial Hydrologic Modeling Extension. So, this is an addition, this software uses ArcGIS and the Spatial Analysis Extension for preparation of hydrologic modeling input data for HEC HMS. So, as you know that huge amount of data is required when we model this infiltration as well as flood routing in a particular catchment. So, we need to give the catchment sizes, the impervious, pervious surfaces, and all the different data sets that has to be introduced, that could be actually put in a GIS framework in this using this particular software. But nowadays we can also use something called a RAS mapper, which would be able to take care of all this. We don't need to have a separate this HEC Geo HMS software. We can just call one component of this HEC HMS, which is this mapper, and using that we can do all this task. So earlier we used to have this separate extension. So the DEM, the digital elevation model, is used to prepare the drainage network and associated data like stream length, elevation, slope, and the longest flow path, centroid location, and so on. So now that we are dealing with open channels and we are going for maybe this 1D equations, Saint Variance equations, so we require a lot of data on the profile of the channel at different sections and so on. And so these are the data that is actually entered into this particular software. Then comes the HEC GeoRS. So this is the same extension, GIS extension for the HEC RS software. And what it helps is it helps in processing geospatial data again in ArcGIS, and this helps in preparation of geometric data for input into HEC RS. So the previous one was preparing data for this we were using preparing data for HEC HMS via HEC Geo HMS. Similarly, in this one, this GeoRS is used for preparing data for HEC RS. And what kind of data is prepared? So this is very important. As you can see that these are the digital terrain model of the river system is prepared in the ArcInfo format. And this is the input data that is required, and then different RS themes are created, which includes the stream central line, flow path central lines, main channel banks, cross section cut lines, land use, levee arrangement, ineffective flow areas, and this storage areas. So the entire channel profile, the entire area is being modeled, along with the digital terrain model is also there. And this HEC GeoRS also takes the data. It can take the data from the other side as well, that is from the HEC RS simulations. Once the simulations are done, the data can be taken in this particular software, and then it can show that water profile, surface profile, or the velocity, and then GIS analysis for floodplain mapping, flood damage computations, ecosystem restoration, flood warning response. These are the things that the software can also display. So this is a two-way thing. We can use this to process the data for input into the HEC RS software, and also take input from the HEC RS software to actually display that particular data. So HEC RS, this is the etc. And this is actually done over here, and then actually could be used in this particular software that is used for computing or running the simulations. So, and instead of HEC GeoRS, we can also use the RS mapper, which is nowadays most convenient. And instead of using both these extensions, this GeoRS and GeoHMS, so we can go for this RS mapper, which can take care of all this. So now let us look into, now that you know about those softwares, let us look into the steps that we actually follow. So in step 1, horizontal coordinate projection is set in the HES RS mapper. Let us go with the HES RS mapper because that is nowadays we can use this to actually do all the different tasks that were done by those two softwares, the geo extension softwares. So in the mapper, it's basically we can do all the maps, but before we start mapping, we have to give a projection, this horizontal coordinate projection system for this particular area. So the second step is to develop a terrain model, that is geometric and hydraulic properties of 2D cells in HES RAS mapper, and this is also required for generating the inundation maps. So what we do is we have the stream channel, and along the side of the stream channel, all this terrain data, with hill shading and contour, based on that we can generate the profiles, And what we do is, we can again when we divide this entire area into different cells, each of these cells will have a particular geometry or this based on that digital elevation model. We create that particular geometric and hydraulic properties of these 2D cells are created, and this will help in determining in which direction the water will flow once we create the inundation maps. So, step 3 is to put in Manning's data, that is using land cover data, we put in Manning's n values for the 2D flow areas, that means wherever the water is going to spread. So, where we put in the Manning's coefficients to understand that what kind of infiltration will happen and so on. So, what kind of values that could be. So, Manning's data is put in over here, and then other information layers such as the aerial photography, levee locations, road network, etc. also are put into this software. So, here we are putting in RS Mapper we can put in the projection system, and here we can put in the land cover classification system, or we can put in the land use data as well. Along with that, we can put in the Manning's this coefficients as well. So, then in step 5 in AGC RAS Mapper, a boundary polygon is drawn for each 2D flow areas that has to be modeled. So, we first determine the extent of the flood that we are going to determine, otherwise it can spread. So, we can define the boundary ourselves. And then in step 6, levees, roads and natural embankments, high ground between main channel and overbank areas, hydraulic structure, etc. introduced as break lines within the 2D flow area. So, within the entire 2D, this is the channel, then we have the entire flow area, then break lines, then levees. This is where the water will not be able to pass through, or at only after certain heights the water will be able to pass through. So, these are introduced as break lines within that area. So, these are boundaries where the water will not be able to directly pass through. Then in step 7, 2D flow area editor is used to create 2D computational mesh. The mesh can be edited as well. So, you can see the mesh of this 2D area. So, this is the 2D, this is the channel, this is the channel, this is the river channel. So, this is the 2D area, and we have created a mesh over here, and as you can see, the computational mesh could be computed by Delanoë triangulation technique, and then we can construct those Voronoi diagrams or those Thyssen polygons that you can see over here. So, that is what has been done for each of this 2D mesh that we are creating. So, basically why we are creating this? So, that we know that each of this mesh will have its own digital elevation, then slope and so on, and when water will flow on the overland surface, it will flow in each direction based on those particular slopes and all. It will flow from one cell, one of this cell in the mesh to the next cell in the next cell which are in the surrounding area. So, that is how it is being computed. So, step 8 is hydraulic structures or bridges can also be added, and step 9 is 2D geometric preprocessor, that is RS Mapper is run to create the cells and face hydraulic property tables, because from the geometric processor we can actually determine based on the digital elevation model of that area, we can determine all the relevant parameters that are required to go into the overland flow model, and that is what is being done in this 2D geometric preprocessor. So, in step 10, 2D flow areas are connected to 1D hydraulic elements. So, the areas, the 2D areas where overland flow will happen is connected with the hydraulic elements, the different nodes from where the flood will be spreading, and then this river reaches lateral, it includes the river reaches lateral structure, storage area of 2D flow area, hydraulic connections, all these things are included in that. Then step 11, external boundary condition lines along the perimeter of 2D flow areas are introduced, and in step 12, the unsteady flow data editor, boundary and initial condition data for 2D flow area is added, and then step 13, we run the simulation in unsteady flow simulation window, and we can compute options, we can change the different options and settings for that. And finally, in step 14, we can combine 1D, 2D output could be seen in the RS mapper, as you can see over here. So, these are very broad steps. Of course, this is much more complicated. You have to first learn the software. So, this software is not covered in this course. I just give you the different steps so that you can understand the basic processes that is happening. So, we have the flow in that particular channel, the water spreads from that channel to the surrounding area. So, to do that, we need to create this, determine the boundary of the overland flow area, and once we do that, we divide this into a mesh and using Voronoi diagrams and all, and once this mesh is determined, then we can determine the properties of this mesh in terms of slope and all the other characteristics, and then we can also introduce, of course, the other levees and all these things in this particular area, this particular overland flow area. And then once this overland flow, this mesh is determined and their hydraulic properties are determined using this this geometric preprocessor, we can generate all this data, and then finally we can use this unsteady flow data editor, and where we use the run simulation for unsteady flow, and we can get the values of how the water will flow along this particular channel, and where it will create floods, where it will come out of the banks and then spread on this particular overland area. And this combined output could be also viewed in the RS mapper. So, this is the steps that we need to follow. So, this I have just not gone into details, I have broadly touched upon this. So, for this you have to really look in some advanced courses, maybe you can look into this 1D, 2D modeling. Whereas, in standard models we can stick to 1D modeling of the channels as well as both surface and underground channels, and then we can model the spread of the flood using some inundation algorithm and using GIS approaches. So, usually we follow that, but we can, in complex cases, we can also go for this kind of modeling. So, let us look at a case study. This is a case study conducted in Mumbai, and this is impacts of land use, land cover change and urbanization on flooding. A case study of Oshiara river basin in Mumbai by Zope, Ildeho and Jyoti Prakash. So, in this model, they tried to determine, in this particular research, they have tried to determine the impact of land use, land cover for a particular for Mumbai, and they studied the Oshiara river basin and saw that how a rainfall event will actually overflow those banks and how flood will spread from that particular river. So, LULC, land use, land cover changes or influences the runoff generation, and due to change in the hydrological processes that we know, and the peak time of flood hydrograph is also reduced, which increases intensity and frequency of flooding. This we have also learned earlier. And flood management in urban areas, we need to understand the flood hydrograph, the flood peak time, that flood peak, the value of the total flow during that time, then time when this happened, and then the floodplain has to be delineated for this particular situation. And then once we have done that, we can also determine the flood damage based on the spread of the flood water. We can determine the flood damage, and we can determine the monetary damage to housing, industry, infrastructure in the floodplain, and also determine based on the level of water the damage would be more. So, that also we can determine. So, we can also do flood hazard zoning maps based on this inundation map that we will get out of this analysis. We can create a flood zoning map, which could take into consideration other data points or other parameters such as flood prone area and probable flooding consequences in that area. Then flood protection measures, warning and evacuation systems could be designed based on that flood hazard zoning map. So, wherever hazard is more, we can consider giving more protection. So, this is the methodology that they have used. So, they have used the initial slope maps, the DM, SRTM data. They also surveyed the area. They have delineated the watershed. They have used the topo sheet satellite images to generate land use, land cover map. They have determined the impervious area, the roughness map, and then they determine the curve numbers, Then they have used the base soil maps and the soil map for different years, hydrological soil group maps. As you know, in the SCS-CNN method, we require this kind of data. That data has come in to generate the curve numbers for this particular area, and then using all these things, they have put that input into the HEC HMS data in the software, and they can actually, and also rainfall input from IDF curves were put in. So all this data goes into this HEC HMS data. So they can, from that they can determine the peak discharges and the flood hydrographs. So wherever that flood happens, they can determine, and then using this HEC GORS and HEC RS, they can actually determine the water surface profile and extent, where 2D approach is used to determine the overland flow from this particular points in the river basin where the flood spread in the surrounding areas. So floodplain modeling for different flow conditions and land use patterns were also done, and finally flood hazard assessment was done for different conditions and different land use patterns. So there they considered the course distance and slope from the river, then Euclidean distance from the coast, because there is also sea, and Euclidean distance from the river. So all these parameters were utilized to determine the overall hazard of flood in this particular area. So for infiltration in this particular software in HEC HMS, the SCS curve number method is utilized, and then SCS unit hydrograph method is actually utilized for determining the hydrograph of that particular area. The routing was done using kinematic wave, and 24-hour storm rainfall was considered, and return period was considered for 2, 10, 25, 50 and 100 years separately. For each return period, the flood inundation was estimated, and then overall map was prepared. So both these two models were used, HEC HMS and HEC RS, and flood hydrographs and peak discharges at each junction for different land use conditions were determined. So that means along the particular river, that Oshiara river, at different points they determined the flood discharge and the flood hydrograph, and the peak discharge was determined, and from there they can estimate the volume of water that will overflow, and that was actually modeled using this HEC RS model. So HEC GORS was used to create the river geometry, left bank, right bank flow paths, cross section cut lines at 100-meter intervals. So this cross section cut lines at 100-meter intervals, and data extracted also from DM. Manning's coefficient was used, and then this HEC RS data, geometric data as input from HEC GORS model was introduced, and in the GORS in this HEC RS software, and 1D hydrodynamic model was utilized for using Saint-Venant's equation, and water surface profiles are generated on that particular Oshiara stream or river, and then boundary conditions, the tidal depth at the outlet, mixed flow condition was simulated, and for return periods of 2, 10, 25, 50 and 100 years. So finally, using HEC RS, the water surface profile and water surface extent was determined, and HEC GORS was used to create water surface, the TIN maps. This is compared with the terrain TIN to create the floodplain polygon. So this terrain TIN was already there, and as you can understand, this is the DM for this particular area, and then they have determined the stream orders, first order, second order, third order streams for this particular catchment area, and this is the land use map that they have prepared, and this is the rainfall that happened, and you can see that for different return periods, for day 1 at different time periods, 12 o'clock, 15 o'clock, 3 o'clock, then 6 o'clock and so on, they have determined that what sort of discharge in meter cube per second happened. So that was determined, and then using this, the water surface, this software, the water surface profile and the water surface extent was determined, and this was determined in form of a TIN map, and then this shows us this this elevation of this water surface, and this was compared with the actual elevation to determine what would be the spread of the floodplain. So the flood hazard map, so once this is the based on the different return periods, the flood depth was determined along the river basin, and this is for a 100-year return period, this is for a 10-year return period. So, according to that, for different return period and for different land use land cover, that is for 1966 flood inundation area and percent area of the total sub basin was determined. Similarly, for 2009 it was determined, and it was found that because of land use land cover change, there is also increase in the flood area by a certain percentage that was estimated over here. So, for 100-year return period, it was showing around 5.61% increase. For a 10-year return period, it was showing a 6.04% increase. So, you can see the flood inundation area is 1.82, it has now become 1.93 square kilometers. So, there is some increase in the flood spread because of land use land cover change. So, flood hazard maps have been created using several parameters, which are like combined floodplain map for different return periods were created, a slope map was generated, then distance from the river, distance from the coast, all these things were considered to create for each of those particular zones. All these parameters were combined to give it a particular score. So, weightages are given to each of these factors to determine the flood hazard zone. So, a score was created for each of those grids, and then it was determined that which has got, based on that we can create a flood hazard map for the entire area, and then further categorization using standard deviation was done to determine that okay, this is a very highly flood prone area, then the next level, and so on. So, that is you can see over here. So, blue is very high prone area, then high is red, moderate is green, violet is low, and so on. So, to conclude, 1D 2D approach uses 2D shallow water equations for surface flow and 1D equations for drainage network. So, that was what we saw in this particular example, and HEC, HMS and HEC RS can be used to determine channel flow and overland flow, catchment inundation for known precipitation events. So, these are the references you can follow. You can do a little bit more study in this, because this lecture is inadequate in the sense it just introduces you to 1D 2D modeling approach, but you need to study it in detail, which you can take it up later. So, thank you.